Hi, I'm Minsoo. I'm going to present depth estimation from a single image using guided deep network. This is a work with Wonjun Kim in DCVL at Konkuk University. We address monocular depth estimation using deep learning-based method. Our method predicts a dense depth map in pixels from the corresponding single input image. The output image on the slide is the depth map result that came out of our model. Then what is the depth map? The depth map is a visual representation which is widely used to interpret the three-dimensional structure of an image by quantifying the degree of close and distant from the photographing system such as camera in the image. Pixel intensities directly correspond to depth values. For a case of the image on the slide, the brighter the pixel, the further it is from the photographing system. Recent advances in convolutional neural network have led to a number of researches on depth estimation. For example, there are iGENS and GANS works as seminal works which adopts a supervised learning using a huge dataset consisting of an input color image and ground truth depth aligned with it. These studies utilize more semantic and global features which is extracted from CNN and outperform traditional methods based on handcrafted features. CNN-based methods differ in how each structure of the neural network are implemented, but in common, input images are encoding and decoding through the network to predict the corresponding depth map. During the training phase, most existing methods perform an optimization process that updates network parameters by only relying on the difference between the final prediction and the ground truth. Therefore, it is difficult to compare how similar the estimated depth map and the ground truth are at the deeper level. To overcome this limitation, we do not just compare the final predicted values and the actual values, but decompose the predicted depth map and ground truth into deeper feature levels to utilize them for optimization. In training, we guide the encoding process of the depth map to the generator via the depth-to-depth autoencoder that restores the input depth map as it is. This allows our generator to produce a more reliable depth map by considering the high-level feature space of the ground truth. These guide processes are performed only in the training phase for loss calculation, and in the test phase, the generator will predict the depth map alone. Specifically, in the training phase, the estimated depth map and ground truth are decomposed into a multiscale feature map through a pre-trained depth-to-depth autoencoder. Feature maps store information to be restored to the original depth map as they are decomposed. The feature map includes high-level and low-level information. The difference between feature components of prediction and ground truth is calculated for each scale and defined as latent loss. This is the comparison results between Goddard and our method on the Kitty dataset. Each image is from the test split and the network had never seen the data. As shown in the results, depth boundaries are clearly restored by the proposed method, whereas the previous method often yields blurry outputs. We also present the generality of the proposed method. We used our pre-trained model on the Kitty dataset without any fine-tuning when applying the model to other datasets. We can see the network provides reliable depth information even in other datasets. Here are the results from Cityscape's dataset. And here are the results from Make3D dataset. This is the video demo comparison between our method and Goddard. Our training and testing code is also available in our GitHub. You can try with your own image to our pre-trained model, or you can train our model from scratch. Thank you for watching this demo.